let's take a look at a couple of applications of this framework that we've set up with hypothesis testing. So suppose we want, generically, we want to test this two-sided framework, that mu is equal to mu naught versus the alternative that mu is not equal to mu naught. Then what we do is we set up our z, and of course later we'll see that if we don't know sigma, we'll put our s in there and we'll do the t, but let's not complicate the argument right now. So we set up our z, let's act as if we know sigma, and then reject if this is too large. Why? Because it's too large. Because then what is z measuring? It's measuring the distance between the observed sample mean and the hypothesized population mean. So if that's too large, we'll say, doesn't look like the data is consonant with the null hypothesis, and probably it's more likely that the alternative hypothesis is correct. So let's look at z. And what we're going to do is reject if z is too large, plus or minus. So we know that this is a standard normal, which means it should be between minus 1.96 and 1.96 95% of the time. So let's say we expect this thing to be what happens 95% of the time. Other than that, we'll go with the alternative, which means that we'll reject if it's bigger than 1.96 or less than minus 1.96. And so we run the risk of rejecting it when it's true of 0.05. So our alpha is 0.05. So there is the generic setup for testing a two-sided hypothesis about the mean. So for example, if we look at, go back to our population, and we stated that the total cholesterol level in our population in Framingham was 237 with a standard deviation of 47.7. Now, I took a sample of 49 non-hypertensives. If I'm not mistaken, I used the random seed from the dollar bill, like before. And what I got was that the sample mean for these hypertensives was 221.9. So the question is, would you believe that this was a sample, can we treat this as a sample of 49 people from such a population? Namely, mean 237, standard deviation 47.7. The formula was calculate your standardized variable, which in this case we observed a sample mean of 221.9, the population mean was 237, standard deviation 47.7, sample size 49, square root of that. Then what we get is minus 2.37, which is less than minus 1.96. So this tells us that this distance between x bar and mu naught, when standardized, is beyond the 95% cutoffs. So we reject the null hypothesis. Minus 2.37 is less than minus 1.96. So on the basis of these 49 non-hypertensives, we get the feeling that we reject the hypothesis that they come from a population with this high a cholesterol level. What you do with that information is up to you, but the formalism of the hypothesis testing makes us reject the null hypothesis. And there is the seed. If you want to repeat what I just did, drop everybody who's hypertensive. That's how I defined it. And then take your sample of size 49, and there's the sample mean. Now, I didn't use the standard error. You could have, had you used that standard error and used the t instead of the z, then this is what you would have gotten as your confidence interval, and that too rejects the 237. The 237 doesn't go in there either. So whether you did the t or the z, Stata does the t. That's how they get this confidence interval. They use the t, but it doesn't matter. So anyway, There are the calculations that I used on the previous slide. So you can repeat them for yourself, but just remember to set the seed. And remember, you don't set the seed every time. By setting the seed, it makes it reproducible so you guys can check out what I did. But if I wanted something truly random, I wouldn't set the seed every time I called the sample. Every time I called the sample command in Stata. In fact, don't do that. Now, some people prefer, rather than say, oh, look, my value is beyond 1.96 or less than minus 1.96, some people prefer quoting what is called the p-value. Now, what the p-value is, the p-value answers the question, what is the probability of getting as large or larger a discrepancy? So remember, we're always looking at this discrepancy between the mean and the sample mean, the population mean and the sample mean. So what's the probability of getting as large or larger a discrepancy? In this case, after we standardize things, dividing by the standard error, we got our value was 2.37. So the question is, what is the probability of getting a deviation as large or larger than 2.37 after we standardize? So because this is a two-sided, that means we want to know probability that our standard Z is bigger than 2.37 or less than minus 2.37. Now remember, the standard normal has got mean 0, standard deviation 1, is symmetric about the origin. So the probability that it's greater than this or less than minus that is the same as 2 times the probability that it's bigger than 2.37. The probability that it's bigger than 2.37 is 0.02222, and I know that from this call to Stata. So 2 times that is 0.044. So the p-value in this case is 0.044, 0.044. And some people quote these p-values and they say, okay, the p-value is 0.044, which is less than 0.05, by the way. So it's less than 0.05, which means I would reject the null hypothesis, because anything that is this rare, I reject. So we have to have a definition of what we mean by rare, otherwise we never reject the null hypothesis. So just like the judge will tell you beyond a reasonable doubt, doesn't tell you what a reasonable doubt means, but there's some understanding that reasonable doubt maybe means 0.95 or something like that. And actually in a civil suit, reasonable becomes preponderance. So then it becomes 0.5. So it has to be bigger than 0.5. So, but anyway, we need some cutoff. And if you're going to go through life looking at 95% or 0.05, then that's your cutoff. You can change it at any time. Of course, change it to better reflect what it is you're deciding. If you're deciding whether to take an umbrella, when you leave home this morning, it's not that big a deal unless you're wearing a really smart suit that was very expensive. Then maybe it is a big deal. But if you're deciding whether you're going to get wet or not, whether to take an umbrella or not, it's a completely different situation than whether you're deciding about medication and a person's life, etc., etc. So it's up to you how you set these critical points. But the 0.05 is quite ubiquitous, and we see it everywhere in science. Here's another example. This time we might be looking at blood glucose level of healthy persons. And if we look at a sample of 64 diabetics, then we know that we are interested in one-sided. Whether it's less than or equal to 9.7, we'll be perfectly happy. But we're concerned about whether it's bigger than 9.7. In this case, of course, it doesn't make any difference, because when I took the sample of 64 of them, their average was 13.1, and when we calculated the Z, it's 13.6, and which is much, much less than 0.001. So whether we did a one-sided or two-sided, that really doesn't make any difference. But there is a big issue about one-sided or two-sided. So set up your Z and then look at your alpha. Suppose your alpha is 0.05. Then the two-sided says reject it if it's bigger than or equal to, in absolute value, 1.96. Now look what happens with the one-sideds. With the one-sided, you would reject, in the one case, if it's less than minus 1.645. In the other case, if it's greater than 1.645, even though your alpha is 0.05. And therein lies the problem. Editors of journals like to publish positive results. They much prefer to write the stories of man bites dog is much more interesting than dog bites man. They don't like, and you can just look in the literature and you can see that this is true, they don't like to publish papers where the null hypothesis is not rejected. All right? So getting a rejection of your null hypothesis makes your results much more interesting, informative, whatever. And if you're doing a one-sided hypothesis, it's much easier to get a rejection than if you're doing a two-sided. Thus, the bias against one-sided hypothesis testing.